to you all. So just one lecture this week. When we come back from Thanksgiving, we have a lecture on that. Yeah, we have lectures the week after Thanksgiving. We'll be doing stochastic methods on that Tuesday, and then non-convex stuff on that Thursday. And then the following week, you have your little test. It's like a multiple choice exam, about the same difficulty as the quizzes, so pretty straightforward. And then the Thursday after that, there's no class, just to work on projects. So that's the rest of the semester. And your homework, your homework 5 is due. I can't remember when it's due. When is it due? Is it due Friday of the week after Thanksgiving? Yeah. Okay, that makes sense, because then you have the weekend to study for the little test. Any questions about the rest of the semester or anything else? Okay, we're going to cover the conditional gradient method today. It's also called the Frank-Wolfe method. Last time we covered coordinate descent. We did not get to screening rules. I could cover about 10 minutes on screening rules, or we could just go on to the Frank-Wolfe method. There's a homework problem on screening rules, but it's completely self-contained. So you don't have to have seen this in order for it to make sense at all. It's just an exercise involving the KKT conditions. And so I guess I'm kind of ambivalent about whether to cover this or not. How many people want to hear this, like 10 minutes or 15 minutes on screening rules? And how many people want to move on to Frank-Wolfe? Okay. Sorry for those of you who didn't want to hear about it. I think we have enough of a consensus that I'm just going to give a few minutes on it. So screening rules are kind of a neat concept. They popped up about, I guess the first reference I have here is from 2010. So that makes 5 years ago. And now there's a lot of papers on screening rules. So every major conference, like NIPS, ICML, AI Stats, etc., I feel like there's at least 1 or 2 submissions on a new screening rule that improves upon the other ones. And the idea is, if I'm doing a problem that involves sparsity, like the lasso, I can also use screening rules for support vector machines, where there's not kind of an explicit sparsity being used, but there's a sparsity in the dual in terms of the support vectors, various other contexts. But let's think about it in terms of a sparse problem like the lasso. The idea is I want a rule that's very cheap to perform, like maybe this requires me to screen through my set of variables and do some cheap operations, that'll give me a bunch of variables as a result that I know are going to have a 0 coefficient at the solution. So I actually can exclude them from the optimization that I perform to find the lasso solution. Okay, so that's called a screening rule. And a safe screening rule, in fact, this rule is itself called SAFE. It was kind of an odd acronym, but this is called the safe screening rule for the lasso, is one such that when I perform it, I get a list of variables that I'm told will have 0 coefficients at the residual at the solution. Then I can exclude those columns from X when I perform the lasso optimization, and I know that I'm guaranteed I have not lost anything. So the solution I get out of the second optimization is the one I would have gotten if I performed a lasso on the full X matrix. And the rule is as follows. I just take, suppose I want to solve the lasso of tuning parameter value lambda. I just take inner products of all of my variables with Y. You can think of these as like correlations of all of my predictors with Y, if these have been standardized. And I look at their absolute value, and I compare it to lambda minus the 2 norm of X times the 2 norm of Y times lambda max minus lambda over lambda max. And let's assume that the data was standardized. Then these would be 1. And lambda max minus lambda over lambda max. Lambda max is the value of lambda at which I get an all 0 lasso solution. So it's the smallest value of lambda at which the solution is just all zeros. I know that as I make lambda larger, I get more and more zeros in the coefficients. At some value of lambda, they're going to be all 0. That's lambda max. Okay, and it turns out that you can explicitly derive that value of lambda. It's just the infinity norm of X transpose Y. So it's the largest inner product of any of the variables with y in absolute value. So this is the comparison. I compare xi transpose y in absolute value to lambda minus, maybe I have those scaling factors, maybe not, this quantity lambda max minus lambda over lambda max. If this passes, then that implies that at the solution, beta hat I is going to be 0. This is the solution to the lasso problem at the value lambda, where I'm using the tuning parameter value lambda. It's kind of remarkable, I think, that this is true, but this is a fact, and it comes from the KKT conditions. So actually, your homework problem is just going to be to verify this, and it involves a bit of work with the KKT conditions and the dual problem. Okay, so a very important note: this is not an if and only if statement. Okay, this is just a sufficient condition. It's not a necessary condition. So, for example, I could have many i's for which this fails. So I could have xi transpose y being bigger than the right-hand side. But it still could be the case that at the solution, beta hat I is 0. I'm not making any claims about necessity. I'm not making any claims that of the arrow going the other direction, just this one direction. Okay, so I could have a million variables. It could be that you know, half of those, half a million, pass this rule, and so I know for sure half a million of the coefficients will be 0. But there could be more than that. There could be still another, you know, 400,000 that are 0, but I just didn't pick up with this rule. Okay, but at least this is a way to whittle down the feature set that I actually passed through the lasso. Right? This can provide a big savings computationally because I'm effectively after this point just using an X matrix with fewer columns. I'm just not even passing those columns into the optimization problem because I know that at the solution, beta hat I is going to be 0. Okay, there have been many advances in screening rules for the lasso. So now they look a lot more complicated than this. But this was the simplest and it was the first, so I wanted to share this one. So in general, this is why I said it's kind of a unfortunate acronym. The word safe screening rule now just means that it's a rule that has this property. So a safe screening rule is just one that if it passes, then we are guaranteed to have a 0 coefficient at the solution. Coefficient at the solution. So safe just means that I can safely eliminate features. I'm never going to be declaring that a coefficient should be 0 at the solution, but actually ends up not being non-zero. That would be something that's not safe. Okay, so safe just refers to this property that I'm guaranteed, mathematically guaranteed, to have a 0 coefficient at the solution. Now there are non-safe rules. And these do not have this guarantee, but they have various guarantees. For example, I may know that with high probability, I have a 0 coefficient at the solution. Or something else, maybe the coefficient is small. At the solution, which maybe means that it has little statistical effect. Right, so excluding that variable may not have been a big deal because in my model for the mean of y, the coefficient may have been small, so it didn't have a big statistical effect. So rules that are of this form there's a few rules. There's one called sure screening. And there's also strong screening. There are some papers on these topics. These are works of optimization. Okay, the safe screening rules, they entirely use the KKT conditions and duality to provide you mathematical guarantees that if you perform these rules, they will give you a set of features that are known to have 0 coefficients at the solution. And has nothing to do with the distribution for the data, nothing to do with statistics. These are pure works of optimization. So they relate most closely to our class, and you're going to prove the first one on the homework. These ones are kind of a mix of optimization and probability and statistics, right? So they don't have precise guarantees in the sense that you know for sure, but some of them have statistical guarantees. Other ones recommend kind of like a second round of checking to check that you didn't actually eliminate features that you shouldn't, etc. Okay, so you might find both, if you're interested in the literature, you might find them both worthy of being looked up. So let me just give you a very basic overview of why the safe rule is true, and then you'll go through the details on your homework. But you can now at least see kind of how, broadly speaking, it will be possible to create such a rule. The construction comes from the dual of the lasso problem, which we've derived a few times. And remember, the dual problem looks like this. It's maximize the Lagrange dual function, which I'm calling g of u, subject to x transpose u and infinity norm being less than or equal to lambda. So to go from the lasso problem, which I didn't write down, but we've written down many other places, to this one is just another exercise in conjugate functions for you guys. And g of u here is 1/2 times the norm of y squared minus 1/2 the norm of y minus u squared. So when we've written the lasso dual before, oftentimes we've dropped this first term because it doesn't depend on u, the dual variable, and we've actually flipped the sign of the second term. So that's probably how you've seen it in previous slides. But this is the dual problem in its kind of exact form, where we have not done those equivalent transformations. Okay, so the idea is, let's suppose that I had a lower bound on the dual optimal value. So I had a value that I knew was smaller than or equal to the maximal achieved value here in the dual. And I'm going to call that, let's call it gamma. And I could get that from just taking a feasible point in the dual, so one that satisfies those inequality constraints, but just isn't optimal. So any feasible point will do. I can evaluate then g at the point u0. G0 is a feasible point, and it gives me a lower bound on the maximal criterion value I can achieve. And because it's a proper lower bound, I can actually put this constraint, I can add a constraint to my dual problem. It says that g of u must be bigger than or equal to gamma, and I haven't changed the problem. Okay, so that doesn't really have any effect on the solution, but it's going to be helpful to us. Okay? So that's what I've done here. And now I'm going to consider computing separately for every I the maximum possible value of xi transpose u subject to g of u being bigger than or equal to gamma. So I'm going to say, let me look just at this constraint set. Forget about the criterion. Just look at this constraint set and ask myself, if I'm going to be staying within this constraint, g of u bigger than or equal to gamma, what's the biggest I can make each individual component of xi transpose u? An absolute value. Okay? And then we're going to call that mi. If mi was smaller than lambda, so if staying within this constraint set, I can only make, let's just say, x1 transpose u at most lambda over 2, an absolute value, then certainly at the solution, at the optimal criterion value, again, I must have x1 transpose u being at most lambda over 2. Because I've thrown away the criterion, and I've asked myself, what's the very biggest I can make x1 transpose u, irregardless of the criterion, over the constraint set? And if the answer was at most lambda over 2, then the same thing has to be true at the solution. Right? If at the solution I have x, say 1 transpose u being less than lambda, then by the relationship between the primal and the dual problems, and this is what you'll verify in the homework, that actually implies that beta 1 is 0 at the solution. Okay, this comes from the KKT conditions, the stationary condition that relates the primal and the dual problems. Okay, so having a strict inequality in that constraint at, say, for a variable I, xi transpose u hat being strictly less than lambda, that implies that beta hat I is equal to 0 at the solution. Okay, so this is the flow of logic. If if the biggest I can make xi transpose u over the constraint set is something smaller than lambda, then the same has to be true at the solution, because this was true for any feasible point. And that in turn implies that the primal coefficient in the ith spot is 0. So that's the idea behind the safe screening rule. OK, here's a picture, more or less. I took this from this first paper on safe rules. And here's the idea. Let's suppose that this was my feasible point. I just picked some theta here that was my feasible point, which was not optimal. Okay, and the optimal point I get from projecting this point here onto the dual constraint set. So that would be, the optimal point would be somewhere here. Okay, this should probably say y. I think for some reason in the notation they use this as theta naught. Think of this as y. The optimal dual point is the projection onto this constraint set. So it's somewhere here. And I just found a feasible point, theta, not necessarily optimal. And you can actually get a feasible point very easily. You can just get a feasible point by taking y and scaling it down so that it lies in this polyhedron. That's what we've done here. And that gives us this lower bound, gamma, on the optimal criterion value. And now I'm going to place the constraint explicitly in the dual that my criterion at my optimal point has to be bigger than or equal to what it was here. So it says the solution has to lie inside this ball, inside this ellipse. Okay? It's an ellipse because G is a quadratic. And that's clearly true. If the solution is the projection of this red point onto the polyhedron, it's certainly inside this ellipse. OK, and now I ask myself, if I stay inside this ellipse, and I try to look at the very biggest I can make each one of the linear constraints that make up the dual polyhedron, are they going to intersect this ellipse or not? OK, if they don't intersect this ellipse, then actually I have that constraint being loose at the solution. So you can see here that if I look at this constraint, then the very, say, closest I can get within the ellipse to this constraint, there's still a gap. That means that if this was x1, x1 transpose u is going to be strictly less than lambda here. The same was true with this linear constraint here. And the same is true with this linear constraint. So here I've safely eliminated 3 linear constraints from the dual. And these ones I can't say anything about. These ones in red here. So essentially, I've now gotten rid of 3 faces that determine my dual polyhedron. And what that means from the KKT conditions is that I have the corresponding elements of my primal solution being equal to 0. So that was kind of like the geometric interpretation of the safe rule. So you'll go through that on your homework, deriving this equivalence and also working with this rule to prove that this rule, indeed, checking mi being strictly less than lambda, is actually exactly this rule. That's what you'll prove on the homework. Okay. Any questions about that? OK, so something to pay attention to if you're interested in sparse problems, because they can provide a huge speed up. You know, you can cut down the feature set by a large fraction by using rules like this. OK. So let's jump over to the conditional gradient methods. Just to tell you which we did last time, to remind you, we looked at coordinate descent, which applied to smooth plus separable functions and performed exact coordinate-wise minimizations over and over again in a sequential fashion, where each coordinate-wise minimization fed into the next. And we talked about how it was a fairly simple method, and it can be surprisingly efficient and scalable if you implement these updates carefully, so that a lot of information is kind of passed from one inner iteration to the next. And we discussed that if it's combined with a pathwise approach, where we solve, suppose you have a hyperparameter for optimization problem, we want to solve the problem over a sequence of values for that hyperparameter, like the tuning parameter in the lasso problem, then utilizing warm starts and also active set tricks, this can take advantage of low-dimensional structure in the problem, sparse problems in particular, and they can be pretty close to state of the art for those problems. Okay, some of the weaknesses or the unknowns of coordinate descent is that it's not always applicable. In particular, when the non-smooth parts don't separate, we can't apply it because we don't have any idea of whether it's going to converge or not. It's not always possible to apply it in the sense that these coordinate updates may not be closed form. So I may not be able to figure out these coordinate updates exactly for the problem that I care about. And it's not generically parallelizable, although people are working to develop versions of coordinate descent that can be parallelized. The one I wrote down isn't, because you have to perform the updates one at a time. The information from the x1 update has to carry forward to the x2 update, has to carry forward to the x3 update, etc. And rates of conversions for cyclic coordinate descent are not really well understood, although they're also something that are being developed right now. So today we're going to talk about conditional gradient. And conditional gradient method only makes sense for constrained problems. So we're going to only be talking about constraint optimization today. If we're talking about unconstrained optimization, then the conditional gradient method is kind of vacuous. It doesn't really give us anything. So it's different from that sense. In that sense, it's different from gradient descent. But we're going to be looking at kind of similar problems as you would have in gradient descent, in the sense that this f is we're going to assume is differentiable and convex. And we're going to have a convex constraint set. And we're going to be comparing conditional gradient to projected gradient descent. Right? Gradient descent is probably the first smooth optimization method we learned. If we had constraint sets, then we saw we could project onto the constraint at every step, and that would still be convergent. Not really. So if the set C is so the projection onto a closed convex set is unique. The projection onto an open set is not really well defined. Yeah. So we're going to be thinking about closed convex sets. So projected gradient descent, remember, it chooses some initial point, and then it makes gradient updates as we would usually. So it just moves in the direction of the negative gradient over and over again. But before that iteration terminates, before we move on to the next one, we have to project onto the constraint set. Okay, so the picture is something like, if this is my constraint set, and I were to take a gradient update, and were to put me here, then I need to project onto the constraint set before I continue to the next iteration. Okay, because otherwise this point wouldn't be feasible. That's projected gradient descent. We repeat that over and over again. The step sizes are chosen as you would normally, using backtracking. And remember that we actually motivated this as a special case of proximal gradient descent, where we replaced that hard constraint with just an indicator function. So we thought about minimizing f of x plus the indicator function for the set C applied to the point x. And this was just proximal gradient applied to that problem. And that was motivated by a quadratic expansion of my function f. So in particular, I can think about the point xk as being derived from the minimization of a quadratic approximation to my function about the point xk minus 1, and then projecting that back onto the constraint set. So here I formed a local quadratic approximation to my function. So this is what I get from taking a first order approximation of my function, and then adding a quadratic term that looks like 1 over 2t times the norm of y minus x squared. Okay, so I make a quadratic approximation where the quadratic form is really the identity, or the identity times 1 over t. I minimize that, and that in turn is exactly this. The minimizer is exactly this, x minus t times grad f, and I have to project that back onto the constraint set. That was the motivation for gradient descent and then projected gradient descent. The conditional gradient method, it's also known as the Frank-Wolfe method. It's named after the two authors, Frank and Wolfe, who proposed this method in 1956. Instead of using a local quadratic expansion, it actually uses a local linear expansion. So that's why I said it goes the opposite direction from gradient descent as Newton's method does. So Newton's method would actually replace this by the quadratic form in the Hessian. So it would make that approximation more sophisticated. It would make a better local approximation. And we saw that, or actually I kind of told you in passing that projected Newton's method wouldn't really work, so forget about the projection for now. But at least compared to the local approximation, it makes Newton's method, tries to make that more sophisticated, a better approximation. Conditional gradient is actually going to drop the quadratic term. So it's just going to make a local linear approximation, so it's less sophisticated than gradient descent itself. And it's going to try to minimize that linear approximation to my function just over the constraint set. And I'm going to call that that S. So S is like an intermediate variable that I keep as part of my Frank-Wolfe iterations. Try to minimize a linear approximation to my function. And if I get rid of all the other terms in that linear approximation, all that matters is grad f transpose S. Right? Because the linear approximation is really f of x plus grad f transpose s minus x. But if I throw out all the terms that don't depend on s, it's just this, grad f transpose s. I minimize that over the constraint set explicitly. That gives me sk minus 1. And instead of then moving just to sk minus 1, instead of me jumping to sk minus 1 as my update, I actually move a bit in the direction suggested by s. So I take a convex combination of where I am now and where I'm supposed to go according to this local linear minimization. Okay, so this is just a little bit less greedy than it would be if we just defined xk to be sk minus 1, which would be the case if gamma k was 1. Okay, so a few notes. There's no projection. The update is solved directly over the constraint set C. So I'm not first trying to find the unconstrained minimizer and projecting onto C. I'm actually finding the constrained minimizer over C. I claim actually that's the only way to do it. Why would it not make sense to first try to minimize a linear approximation to my function and then project it onto C? Right, so minimizing a linear function doesn't make any sense, right? Because the minimizer is going to be off at infinity somewhere. So I have to actually constrain the problem, otherwise to the variable to lie within the set C. Otherwise, it wouldn't make sense. This is why I said Frank-Wolfe with no constraints is ill-defined, okay? Because this wouldn't make any sense. I can't make a local linear approximation to my function and expect to minimize it and have anything meaningful happening. I can if I'm actually if I have constraints to my problem and I keep those constraints in when I form that local linear approximation, which is what's happening here. Okay, and the second note is that instead of jumping right to sk minus 1, I take a step in the direction of sk minus 1. So this gamma k is a step size, just like we would use in gradient descent. And there's default choices for the step sizes. And like the subgradient method, they're not adaptive. So they don't depend on a Lipschitz constant for my function. I don't do backtracking line search by default. I just take a fixed choice of step size, which is 2 over k plus 1. That happens to work well. And we're going to see later on that with this choice, we get a convergence rate for Frank-Wolfe that's very much like gradient descent. No, this has nothing to do with acceleration. So it may look a bit like acceleration transparently because I'm adding 2 terms, but that's just similarity in the way it's written. So there are many addendums to Frank-Wolfe that we'll cover later on, many additions you can make or modifications. Like we could, for example, do step size optimization instead of just choosing these fixed step sizes. We could do a bunch of different things. Like, for example, we could get away with inexact updates here, inexact solutions to this constrained to this constrained problem here. But we'll cover those later. Just for now, think about I can solve this first step exactly, and I choose gamma k to be 2 over k plus 1, and I update according to that rule. I can also think of this rule as I'm taking xk, I'm defining it to be xk minus 1 plus a step size gamma k times the direction suggested by this update. So I'm moving in this direction, s minus x. So this being the minimizer of my linear approximation of my function over c. this being where I was before, and that being my step size. You can think about that as the Frank-Wolfe algorithm as well. Okay. Any questions about that? We're going to see lots of examples, so it'll become more concrete. Okay, this was a picture from, so this is a very old method. This method was first written about by Frank-Wolfe in 1956, although I think probably even earlier people had thought about local linear approximations. But recently, Martin Jaggi, who's a machine learning researcher, he kind of brought it back to up to one of interest. He brought it back to being a method of interest within the machine learning community when he wrote this paper in 2011. And his thesis was actually all about this topic because we can see, we'll see shortly, it actually provides, in some cases, much cheaper updates than even proximal gradient. So it can be much cheaper on a per iteration basis than proximal gradient would be, or projected gradient. Okay, and this picture is trying to tell the story where I have this function f. I have some constraint set. He calls it d in this picture. I'm at the point x, and I make a linear approximation to my function. That's this plane. And I ask myself, over the constraint set, where is this linear function being made smallest? And that's this point s. Okay, if we didn't actually look at the, if we didn't actually constrain ourselves to looking at the set d, when we ask the question of how do we minimize this linear approximation to our function, we'd end up somewhere out here, right, which would be ill-defined, somewhere off in infinity. But with the constraint set in place, this is s. And instead of jumping from x to s, we just move a bit in the direction of s, right, per this update. Take a convex combination of x and s and end up here. And then make the same perform the same story. Make another approximation to my function that's linear. Ask where is it made smallest over the constraint set. Move a bit in the direction of that point. So that's the story behind Frank-Wolfe. Okay, let's go through a bunch of examples and see. We're going to see that actually, for various problems, these Frank-Wolfe updates can be done in closed form, and they're actually pretty cheap. First thing we'll look at is when C is a norm ball. So C is the set of all x for which the norm of x in some norm, this could be an LP norm, this could be a matrix norm, x could be a matrix, just some norm, is less than or equal to t, where t is a fixed constant. Okay, you can think of it like it's our tuning parameter actually as part of the problem. But with respect to the optimization problem, it's just fixed. So by definition, this first step, right, in Frank-Wolfe, it has us optimize over the set of all vectors s that have norm at most t, this quantity, the grad f transpose s. And this is a constant with respect to this optimization, right? This is just some vector transpose s. So we want to find the s that makes that the smallest possible. So I can rewrite that. Okay, I can rewrite that as just, first I'm going to change the argmin to an argmax. And I'm going to put a minus sign. So the thing that makes this the smallest is the negative of the thing that makes this the biggest. And then I'm going to actually change the constraint set to being the norm of s being less than or equal to 1 and pull out a t. Why can I do that? Because any vector that has norm at most t, I can write that as, let's say, t times z, where z has norm at most 1. And so I've just reparameterized the problem now to be in terms of z. So this is grad transpose z, and I've pulled out the leading t. Okay, so this is just a few simple manipulations for me to get from here to here. So now I want to solve this problem, argmax of grad f transpose s over all vectors that have norm at most 1. But you guys know what that is. Okay, that is, you should recognize when you see this, nothing else than the subgradients of the dual norm evaluated at whatever this vector is. So remember, we have the dual norm of some norm evaluated at a point x is equal to the maximum over all vectors z that have norm at most 1 of x transpose z. It's the definition of a dual norm. And the subgradients of my dual norm evaluated at the point x are the things that achieve this maximum. Right? They are the z's that make this the biggest. Yeah?
There, where you're going from having t in the constraint of s and having it in the objective function, can we always do that? Like rescaling the constraint set and rescaling the objective function by the same factor?
It depends. So yeah, in principle we could, but it depends on whether that's analytically tractable, right? So here I know that I'm just using the property that if I take the norm of t times z, that's just, if t is positive, right, that's just t times the norm of z. And that's the property of norms, right? Positive homogeneity, or whatever it's called. So it makes it so that I could rewrite this constraint being less than or equal to 1. If I have an arbitrary constraint set and I want to scale it by a constant, that may be possible if I have the constraint set written out in terms of a norm. But if I have it written out in terms of functions, like some functions being less than or equal to 0, then it may be hard to know what that means to scale it by something. So it just depends on the problem. Good question. Yeah?
We said the gradient of the function is just going to be some constant.
Right.
So if I do the subgradient of the dual norm of that, is that again just going to be some constant?
So
is that similar to some soft threshold?
Right. So yeah, we're going to, good question. We'll get to a bunch of examples. But the takeaway here is that suppose I gave you a norm that whose dual norm you knew and whose subgradients you knew. Then as long as you know that prescription, you're just evaluating, you're just taking subgradients over and over again at a different point. That point is just the gradient of my criterion function. So, right, let's suppose I had an L infinity norm constraint. Its dual is the L1 norm. We know the subgradients of the L1 norm, they're just the signs of the non-zero components. And if I have a 0 component, it's anything between -1 and 1. I'm just applying that rule over and over again to the gradient vector to get the update. And so we'll go through some examples of that. Right, so just to repeat, if I knew the dual norm, and I knew what its subgradients were, then I can easily perform the Frank-Wolfe steps. I'm just evaluating the subgradient at a different point here, that point being the gradient of f. Okay, so the key to Frank-Wolfe is that it can often be simpler or cheaper to perform something like this, or even if we don't have a norm, it can often be simpler or cheaper to perform the Frank-Wolfe update than it can be to project onto my constraint set. Okay, projection can be expensive. It also can be something we don't know quite how to do. This, it turns out, for a bunch of problems we're interested in, is something that we can do often in closed form, and it can be cheaper than projections. It's also often simpler or cheaper than the prox operator for a norm, say. So we'll talk about that as well. Let's just go through a bunch of examples. I think it'll help. Let's talk about L1 regularization. Okay, so if I had a problem minimizing some smooth function subject to an L1 norm constraint, the dual of the L1 norm is the L infinity norm. And in order to perform Frank-Wolfe updates, I have to know what the subgradients are of the L infinity norm. Because at any point, I have to actually take the subgradient of the L infinity norm, evaluate it at the gradient of my criterion function, and multiply by -t, and that'll give me the update direction. Right, it's easy to see that a valid subgradient of the L infinity norm is just a vector that has all zeros, and it has a 1 or a -1 in the spot where the maximum is achieved. Okay, so if I have, let's suppose I have that the L infinity norm of a vector x is equal to the absolute value of xi. In other words, I'm just telling you, suppose you knew that ith component achieved the max. So if we have that, then this vector, sine of xi times ei, is in the subdifferential of the L infinity norm at x. EI here is the vector that has all zeros, then has a 1 in the ith spot. Okay, that's something you can either recall from our lectures on subgradients, or you can derive as well. Okay, so all I'm doing here is I'm taking the component of the gradient that was the largest in absolute value. I'm calling that ik minus 1. And a subgradient is going to be minus t times the sign of this maximum guy times the vector e ik minus 1, which was this ith standard basis vector, right? Just that all zeros, but then a 1 in this spot, ik minus 1. And I'm taking a convex combination of my current point with this update. And what it looks like is just greedy coordinate descent. I found the component of the gradient that was largest, and I've moved a bit in the direction of the negative gradient for that component, leaving all other components untouched. Okay, so this is really just like a greedy version of coordinate descent. We're actually taking specific step size choices as well. Okay, so the thing to note, this is a lot simpler than projection onto the L1 vol. This is code that you can write in any language, right? I just have to know how to find the maximum of a vector, and I'm just making a very simple update to one component of my optimization variable x. And projection onto the L1 vol is actually pretty non-trivial. You guys had a homework problem on that that reduced it to something that could be done with a sort, so it could be n log n, or you can do it more intelligently if you kind of keep track of various quantities. But this is like a research level topic. There are papers on how to project onto the L1 vol in order n time. This is something you can implement, in 30 seconds in any language of your choosing. So it's big difference in terms of sophistication. It's also cheaper to perform that than projection, even though they're both linear time. Okay, let's talk about LP regularization now. Just briefly, if I replace the L infinity norm here by an LP norm, or sorry, the L1 norm here by an LP norm, then I claim that the following is a valid subgradient of the LQ norm evaluated at the point grad f. Okay, so the dual of the LP norm is the LQ norm, where 1 over p plus 1 over q is 1. I claim that this is a valid subgradient of the LQ norm at the point grad f. So I'll leave you guys to check that. You can just plug this into the formula for subgradients and check that we get the right inequality. You can also plug this into this maximization problem and just check that we actually have achieved the max. But that's a valid subgradient. Look, it's just a bunch of simple arithmetic operations. I have to just raise each power of my absolute gradient to some, so each component of my absolute gradient to some power and multiply by some constant times the sign. And then I just update the Frank-Wolfe iterate x as usual. I just move in some direction given by the convex combination of x and this point. That's my Frank-Wolfe update. Okay, so again, they're fairly simple. This just requires very simple arithmetic to compute, and it's much, much simpler than projecting onto an LP vol, in particular because we don't know how to project onto LP vols unless p is 1, 2, or infinity. So if I gave you this problem where p was 3, you would probably have to do some kind of, if you wanted to use a first order method, you'd have to do some kind of inner optimization to figure out that projection. Maybe you would do something that involved interior point methods or something. But here you can make these Frank-Wolfe updates in closed form. A few more examples. Let's look at another norm, but now applied to a matrix variable. Suppose we had a trace norm constrained problem. So remember, the trace norm of a matrix is the sum of the singular values. Okay, let's suppose we had this problem, and we wanted to perform the Frank-Wolfe updates here. We would just use the fact that the dual of the trace norm is the operator norm, so it's the largest singular value. And subgradients of the operator norm are something that you guys derived on a homework. And I seem to remember it being on a practice midterm as well. you can derive the subgradients of the operator norm just from the definition. And a valid subgradient of the operator norm of x is just uv transpose, where u and v are the top left and right singular vectors of x. Okay, so I take x, I find its top left and right singular vectors, I take their outer product, that's uv transpose, and my Frank-Wolfe update is minus t times whatever that is, minus t times the subgradient. So it's minus t times uv, and all I do is I take x, and I take some convex combination of x and this guy, minus t times uv transpose, and that's my update. So it's more expensive than these two, right? Certainly more expensive than L1 constraints, because it requires us to find some spectral information about x, namely its top left and right singular vectors. But we're not having to do a full SVD. It's just the top left and right singular vectors. So that can be done quite cheaply with the power method or a variant of the power method, for example, if you've heard of that. Okay, so the take home, again, is it's a lot simpler. It's much more efficient than projection onto the trace norm ball. If you want to project onto the trace norm ball, that's an exercise you can try to write out on a piece of paper. You guys can do that now with your knowledge of convex analysis. You can prove that projecting on the trace norm ball actually requires a full SVD, whereas this only requires knowing the top singular vectors, top left and right singular vectors. Okay, so those were 3 examples of norm-constrained problems where Frank-Wolfe kind of gave us a lot more than we would get from first-order methods.
Is there any ballpark figure where, so a lot of people do trace norm regularization with the SVD, or they do partial SVD, something like that.
Right.
Would there be a ballpark figure for what size of X this might be the better way to go, or is this always a better way?
Yeah, good question. So we'll come to the convergence of Frank-Wolfe versus first-order methods in a bit. I'll just say now that they have the same convergence rates, so they have the same guarantees. In practice, I think I found, and I think that most people would agree with this, they tend to make much less progress per iteration. So the iterations are a lot cheaper. They tend to converge less quickly in practice. So it's worth trying for sure, but I think that first-order methods, there's something in these convergence analyses that is not very tight, because first-order methods still seem to perform a little better in terms of their convergence rates. Okay, just to finish off this sequence of examples, and then we'll take a break. We've talked about all the constrained forms of these problems, right? L1 constraints, LP constraints, trace norm constraints. Of course, we know from our lecture on KKT conditions, and also just from the fact that we would have seen this a lot in the literature, that any constrained problem can be transformed into a Lagrange form problem. In particular, that's true for norms. And if I want to solve this problem over a sequence of t's, I don't really have a particular value of t in mind, I get the same thing by solving this over a sequence of lambda values, more or less, because every solution here for a particular t can be gotten from a solution here for a particular lambda. So if I'm thinking about this problem from the perspective of statistical analysis or machine learning analysis, I would solve just whichever one's easier, right? I wouldn't just stick to the constrained form. I would just say which one is easier. So what I should really compare Frank-Wolfe to is either projected gradient or proximal gradient, because I probably wouldn't do projected gradient if I knew how to do the prox operator, right? Or vice versa. I would just choose whichever one's easiest for in my particular case. And so let's compare the Frank-Wolfe updates to the updates for this problem. And those are going to be proximal gradient updates where the prox operator is driven by just this norm. What's the prox of my norm? So how about the prox of the L1 norm? Frank-Wolfe, it scans for the maximum absolute value of the gradient. The proximal operator soft thresholds every component of the gradient. Both are equally simple. Both are order n. So even though we said that projection onto the L1 ball was maybe a little harder, the fair comparison is probably really, in this case, to the proximal operator of the L1 norm. And that's just as simple as the Frank-Wolfe update. Okay, so there's really no difference there. How about the LP norm for a general P? The Frank-Wolfe update, remember we saw that it took every power of every component of the gradient, raised it to some power, and then scaled them. That's order n. The prox operator is not generically computable for the LP norm beyond, again, the cases say 1, 2, or infinity. So again, we have an advantage here. I don't know the projection operator onto the LP ball. I also don't know the proximal operator for the LP norm for a general P. And the trace norm is also in Frank-Wolfe's favor. The Frank-Wolfe updates just reduced to the top left and right singular vectors. The proximal operator for the trace norm, we actually derived this in class. It requires an SVD, just like projection does. Now, to be fair, those SVDs in practice are usually, they're done partially, because you can kind of compute bigger and bigger pieces of the SVD until you get to a point where you don't need the full SVD. But still, it's a lot more than just computing the top left and right singular vectors. Right? That's just one step of a power. That's just a power iteration, for example. I can get that from the power methods. So there's many other regularizers. So if I replace this norm by a function g that yield efficient Frank-Wolfe updates, for example, special polyhedra or cone constraints, some of norms problems like the group problems we saw, atomic norms, there's a bunch of others. So you can take a look at this paper or the thesis from Martin Jaggi to get a sense for the other problems that are solvable. OK, any questions about this?
Why is the projection of the L1 norm takes O and 16? Is there anywhere talking about that? I think it's the log.
So in your homework, we walked you through a solution that was n log n. But you can liken the problem to finding the median of a data set. And the naive way to find the median is to sort and to pick the middle element. There's also a worst case linear time median algorithm that keeps track of kind of careful quantities. The projection onto the L1 norm can also be done in order n by keeping track of careful quantities. So there's a paper by John Ducci on this topic. It's just called linear time projection L1 ball. I would just look up that stuff. It's by John Ducci, D-U-C-H-I, from 2009. So, other questions? OK, let's take a break, and then we'll come back and discuss some other properties.